Okay, so just a quick run through demo to show what I'm doing with the dielectrophoretic separation tutorial in COMSOL, and just to show the overall idea of how we could use this with sea salt brines and for what I'm doing for my thesis. So now this is, red blood cells and platelets, but there's nothing in this that won't allow for us to use this for if you have ions in seawater with a hydration shell. It will work exactly the same because they're considered like a solid particle with the charge density, permittivity, and the relative permittivity also of the surrounding fluid, which is water, seawater in this case. It's 81 permittivity instead of 80. Conductivity, those kind of things we have to deal with too. But I just want to show you briefly. Okay, so here's our geometry and electric currents. So maybe it's just better if I show you. So I want to first show you the channel. So this is a micro channel, and as you can see, it's in micrometers, so very small. And you have your positive, negative, positive, negative. It's negative 5 and positive 5 volts, and the frequency is I think it's 1 kilohertz, maybe 10 kilohertz. So you can see they will come out here, this inlet, and out through these two. So they will go through these. There's no membrane or anything involved. And I'm going to show you without the dielectrophoretic force. So they come in through here. There's more coming in through here at a higher velocity, actually. So without the dielectrophoretic force, you can see they just kind of go along the top because this is moving at a higher velocity, and these, in this case, platelets and red blood cells come along the top, and they go out the top one. Now, study 3, this has the dielectrophoretic force. So you can see the fields and how these end up getting separated. The red blood cells go out through the bottom, and the platelets go out through the top. And so, in a simplified manner, you're using electric fields and the inherent electric properties of the molecules to act. In this case, I mean, it's more than molecules, but just to give you an idea, you can use this to separate them. And what I found when I went through and change the electric potential, so as you can see here, we have these electric potentials. Let's change it to 50 volts. Okay, so these are going to be positive 50 volts. These others are going to be negative 5. We're going to leave it there. And so we have to run the studies again. There's a couple of things we have to do. Maybe I should have just done update solution, but I'll go ahead and do compute. All right, and again, we'll run study 2, no dielectrophoretic force. So as you can see, they go out, they kind of stay on the top because it's faster down here. This is not exactly what we're doing with sea brine, but it's similar enough. But so you saw before, and now we're going to show you with the changed voltage. We just changed the positive voltage to 50, and now you can see the change in behavior. Now just the platelets are actually coming through, and they start going down this tube. So there's a lot we can do with this, with geometry. Even, this is just one pulse. I think it's 10 kilohertz. And but if we had different pulses, and some of it even, DC, AC, in different geometries, we could use low power, if it's high voltage, low current, to selectively migrate different ions in seawater brines and even wastewater brines. And we can do it without membranes. And it's low power. We're just changing the electric field, and we'll migrate these. We might be able to migrate some towards the boundary layer at the top because we want them to crystallize, and others we want to push down. Say like sodium chloride, we want to push those down, and we want to raise up magnesium. It's going to have some chloride or some sulfate with it, probably sulfate in that case. But so this is just kind of a brief explanation so you can see what I'm doing. This doesn't touch on evaporation, but that's a different simulation.